All right, ladies, so for this snow day activity, we're actually going to be taking a look at a formula called the vertical motion formula. So if you haven't watched video 1 yet, you need to do that. We're going to reference it. And if you're joining us for video 2, you are going to need your notebooks. So hit pause on your video, go get your notebooks and a writing utensil, and I will see you back in a short second. All right, so on the top of your notebooks, I need you to label it as 5.44 vertical motion formula. And this formula is really derived from this idea that people discovered that they could predict the length of time an object was in the air based on this formula. And it has to do with the fact of like how fast is something going and what height is it starting at and gravity, really. Those are really the big factors in this formula. So first I'm going to write it out. Y is equal to negative 1/2 a t squared plus b little o t plus h little o. And I don't know about you, but I would like to define all these variables. So y is really just the height, and the height can change over time. Sometimes it could be all the way up in the air. Here, let's draw a little sketch of what we're going to be talking about. We're going to be talking about a bottle rocket, but your height changes depending on how much time has gone by, right? Here it's going up, and then eventually it starts coming back down. So y is this changing height. Half, it's a value, okay. A is your acceleration due to gravity. Acceleration, acceleration, due to gravity. All right, so this is where it gets kind of neat. So we actually measure any of the problems that we're doing either in meters or in feet. So those tend to be our two primary systems of measurements. So we need to account for both of those systems. Gravity comes to the ground at a rate of 9.8 meters per second squared. So this is really in the metric system. And then over here in the, I think it's American, could be wrong about that, the American system, we're looking at a 32 feet per second squared. Now, if you were to drop a marble off of a really tall building and you both released it at the same time, one measured the time it took thinking about it being launched at 32 feet per second and the other person thought about it in terms of meters per second, it would be the same thing. They're actually identical. Nobody moves faster than the other. But they do come into play when we're trying to figure out time based on the unit of measurements that were collected at the time of that date. So in our word problem, they're going to tell us something like this. They're going to say, hey, I have decided to launch a paper rocket into the air, and I want to know a little bit of data about it. And you're like, hey, I have math class. I'm totally ready for it. So she says, all right, so I've built, here, I'll show you what it looks like. They built that, okay? And they want to know, is or when will this object actually reach a height of 490, listen for the units, will it reach 490 meters? So that's our first thing. That's my question. 490 meters, right? They also give me another piece of information, which was that the initial velocity, this thing is grooving, is at 125 meters per second. This is our velocity, our very initial velocity. All right, so I'm hoping you're standing with me here. If not, take pause. Feel free to go back. Right now, we're going to try to predict the time when our parabolic motion, whatever is being sent, will be we're looking to see when it's 490 meters, and I'm wondering if there's two locations for that to happen, but we won't know until we do the math. All right, so what we got? Y is equal to, because we're in meters, we're going to replace it with this. I personally like to do the half times the unit of measurement almost all in one. So half of 9.8 is 4.9, and I'll just maintain the negative. So this is going to be negative 4.9. And I'm not going to use the units of measurement for now. T squared, right, because that's the question unknown, plus our initial velocity is 125 meters per second. Oh, sorry, I lied. The initial velocity is actually 122.5. Yeah, that's going to make a huge difference. It's actually 122.5. My apologies on that. I just checked over on my screen. All right. And then on this guy, the initial height was really 0. It's being launched right from the ground. All right, so what are we going to do? I want to know when the height, which is y, is going to reach 490. So I'm going to set 490 equal to negative 4.9 t squared plus 122.5 t plus 0. And then I'm going to move over the 490. I have negative 4.9 t squared plus 122.5 t, and then minus 490. And then this is going to be set equal to 0. All right, messy numbers, but we know that if we get the lucky opportunity of being allowed to divide out our leading coefficient, we're going to be in like really good shape. So that's what I'm going to try. I'm going to try to divide out a coefficient from each one of these terms. So what do we get? 0 is equal to t squared plus, I'm going to have to consult the math goddess. So I'm going to divide this by 4.9, and it seems like we're getting out the number. Here we go. 25. So it seems like we're getting out the number 25. So 122.5 divided by negative 4.9. It's actually going to give us a negative value of 25. And then the t. And then finally, negative 490 divided by negative 4.9. That looks like a positive 100 to me. This problem's a lot easier to factor and solve, is it not? So as I go through, I think, let's see, 100 is 20 times 5. Number 100 is 20 times 5. There's also 25 times 4. These are generally kind of the big ones. And I think we can make a 25 out of a 20 and a 5. All right, so t plus, really it's minus, right? Because I want to make a minus 25. T minus 20 times t minus 5 should give me 0. And then let's just follow it up with the t chart. T minus 20 equals 0. T minus 5 equals 0. So we're looking at a time of 5 seconds. We're looking at a time of 20 seconds. And yeah, that should kind of make sense to our sketch. So what's going to happen? After 5 meters, our rocket will reach a height of 490. So after 5, we call this 5. After 5 seconds, really, we will reach a height of 490. But the problem still has some ways to go. And when it gets to the equal but opposite location, which is, let's say it told us 20 meters away, or not 20 meters, 20 seconds away. So 20 seconds after this hit, it's going to come back down. 20 seconds after that, we know that it's going to be at a height of 490. All right. Hopefully that made sense to you. Major concepts. You have this formula that will allow you to predict time of projectile motion. How long will it be in the air for? And it just depends on whether or not you're using the metric system or the American system. And I'm going to give you 2 problems for homework tonight. Do as much as you can and just kind of solidify the concepts. All right? Have a good one, ladies.